Start by understanding the fundamental types of covalent bonds, sigma and pi bonds. A sigma bond forms when atomic orbitals overlap directly along the axis connecting two nuclei. This can happen with SS, sp, or pp orbital overlaps, making sigma bonds the strongest type of covalent bond. For example, in molecules like C2H2 and C2H4, sigma bonds are responsible for holding the atoms together along the main axis. Contrast, pi bonds are formed by the sideways overlap of p or d orbitals, resulting in electron clouds above and below the plane of the nuclei. Pi bonds are generally weaker than sigma bonds and restrict rotation around the bond axis. Understanding these two types of bonds is crucial for grasping molecular structure and reactivity, as they determine the strength and flexibility of chemical bonds in molecules. Now let's explore hybridization and how it shapes molecules. Hybridization is the process where atomic orbitals mix to form new hybrid orbitals with equal energy and symmetrical shapes. This concept helps explain why molecules have specific geometries. For instance, in methane CH4, carbon undergoes sp3 hybridization, forming four equivalent bonds arranged tetrahedrally. Other molecules like BCl2 and BCl3 show linear and trigonal planar shapes due to sp and sp2 hybridization, respectively. The type of hybridization depends on the number and arrangement of electron pairs around the central atom. This not only determines the bond angles but also the overall geometry of the molecule, which is essential for predicting chemical behavior and reactivity. Understanding hybridization gives us a powerful tool to visualize and predict molecular shapes. Next, let's look at some important bond properties and theories. Bond order tells us about bond strength and stability. The higher the bond order, the stronger the bond. For example, N2 has a bond order of 3, making it very stable. The octet rule explains why atoms form bonds. They seek to achieve 8 electrons in their outer shell like noble gases. However, there are exceptions, such as molecules with odd numbers of electrons or expanded octet. Concept of resonance helps us understand molecules like carbonate ion, where the actual structure is a hybrid of multiple Lewis structures. Finally, molecular orbital theory explains why some molecules like B2 don't exist due to zero bond order. These concepts together provide a comprehensive framework for understanding why molecules form, their shapes, and their chemical properties. Let's not forget about hydrogen bonding and dipole moments, which play a crucial role in molecular interactions. Hydrogen bonds form when a hydrogen atom bonded to a highly electronegative atom like oxygen or nitrogen interacts with another electronegative atom. These bonds are stronger than van der Waals forces but weaker than covalent bonds. Hydrogen bonding is responsible for many unique properties of water, such as its high boiling point. Dipole moment measures the polarity of a molecule, indicating how electrons are distributed. Molecules like H2O have a significant dipole moment due to their bent shape, while CO2, despite being triatomic, has zero dipole moment because of its linear geometry. Understanding these concepts helps explain the physical properties and reactivity of molecules in chemistry and biology. Wrap up, we've covered the essential concepts of chemical bonding: sigma and pi bonds, hybridization, bond order, resonance, and hydrogen bonding. Each concept builds on the previous one, helping us understand why molecules form the shapes they do and how their properties arise. Whether it's the strength of a triple bond in nitrogen, the geometry of methane, or the polarity of water, these ideas are foundational for chemistry. Mastering them not only helps in academic studies but also in understanding the molecular world around us. Keep exploring these concepts and you'll find that the language of chemistry becomes much clearer and more intuitive.